Hey, my name's Naveen, and today I'm going to be talking about my black hole lab. So, introduction. The purpose of the lab is basically to estimate the mass of a black hole using Newton's law of gravitation and the momentum principle. The only data we're given is the position data of a star that's being affected by the black hole. So, the only force in the system is the gravitational force between the black hole and the star. And here are just the equations for the momentum principle and the Newton's law of gravitation. So the modifications I made to the code, the initial conditions, I set the mass of the star to be 2 times 10 to the 30th, which was the given value for the mass of the star. And then delta t is 1 day, which is just 86,400 seconds. And I changed g, the gravitational constant, to be 6.7 e to the negative 11th. So this is the next part of the code I modified. I changed p initial to be star.m times v initial, and then p final to be star.m times v final. And then just delta v is the final velocity minus initial velocity. Delta p is final momentum minus initial momentum. And dp dt is just delta p over delta t. I changed this f net equals to dp dt. This comes from the momentum principle. And finding p hat. P hat is basically the unit vector that points in the direction of momentum parallel to the motion of the star. And this, I basically found the unit vector, so I can define dp dt parallel as the magnitude of the change in momentum times p hat, the unit vector pointing in the direction of the momentum parallel to the motion of the star. And now that I found dp dt parallel, I can find f net parallel, which is the same thing as dp dt parallel. And then to find dp dt perpendicular, dp dt perpendicular and dp dt parallel are just both components of dp dt. So you can find dp dt perpendicular by subtracting dp dt parallel from dp dt, and that's what I did. And then again, f net perpendicular is just dp dt perpendicular, since net force and dp dt are the same thing. So for the next part of the code that I modified, I changed these lines to find the mass of the black hole. You find r using position data, just the magnitude of the distance between the star and the origin, which is the black hole. And then you solve for the mass of the black hole using Newton's law of gravitation. For the aeroscale part of the code, I had to experiment with the aeroscale value. I started at 1 times 10 to the negative 30th, and that was way too small. I couldn't really see the arrow, so I just kept going up by 1 exponent each time. So I went from negative 30 to negative 29, negative 28, until eventually I got to negative 17, and it seemed like the right value. When I ran the program, the arrows showed up pretty clearly, so I settled on e to the negative 17th. Conclusions. So I plugged all the mass data into Excel and used the average function to find the average of my black hole mass. The value fluctuates between each position data value point, just due to like small decimal errors. And I found my average black hole mass to be 1.86 times 10 to the 34th. So yeah. What does this mean? So the original question was, are the components of net force and dp dt equivalent? And I said yes. The rate of change in momentum and the net force are equivalent because of the momentum principle, which is derived from Newton's second law. The parallel and perpendicular components of each value are also equivalent. In the lab, we used the momentum data to solve for gravitational force, but we could also use force data to predict an object's motion. What if a different black hole was used, but the position data remained the same? And then we're also assuming that F-grav is still the only force acting on the star. If the position data remained the same, that must mean the gravitational force also remained the same between the star and the black hole, and that means the mass values, the initial mass values, were also the same, which means that the mass of the new black hole is the same as the original black hole. So, yeah.